Okay, hi guys. I'm going to get started. I've just had a few issues with getting connected up today, so I can't seem to get it to display in the usual way. So I'm not able to show you my calculator whilst I'm doing this. For some reason, it just will not work today, but I think a lot of this is algebraic anyway. There's not a huge amount that can be done on the calculator. So it's our first day of doing some excellence practice in the lead up to the exam. Okay, so let's start with this complex numbers question. We've got u is 6 plus ki and v is k plus I, and find k if the argument is pi by 4. Now, that being pi by 4 is a really important detail. It means that we have an isosceles triangle on our Argand diagram. So let's first of all start off by doing u times v. So 6 plus ki times 4 plus ki, and we're just expanding that bracket there. So if we do 6 times 4, we're going to get 24. And then the 6 times the ki is going to be 6ki. The 4 times the ki. And then we have k squared, I squared. Okay, those of you that are watching, just let me know if there's any issues with this coming through. I'm not trusting the technology today, so just pop something into the chat if anything is amiss. Okay, so then from here we know that I squared becomes minus 1, so we have 24 minus k squared, collecting up the real terms together. And then we also have 6k plus ki, so that becomes 7ki. Wait, I missed out the 4, didn't I? Okay, so I think just there, that should have been the 4. So then 6 plus 4 is 10ki. So apologies for that one. But just on the expansion in the middle there, I'd accidentally written it down without the 4 in it. Okay, so we now have u times v. Now we're told that the argument that makes will be pi by 4. So if we plot that onto an Argand diagram, we have some point out here. This will be uv. The argument that we make is pi by 4, the same as 90 degrees. So what we end up with is an isosceles triangle. The real part is 24 minus k squared, and the imaginary part is 10k in the I direction. Now, if that's an isosceles triangle, those two parts will be equal. So we have 24 minus k squared is equal to 10k. Now, turning that into a more regular looking quadratic, just putting it into order and all on the same side of the equal sign, we will end up with this. Now that factorizes quite nicely. We have k equals 2 and k minus 2 and k plus 12. So k equals 2 or k equals minus 12. Now, the one thing that I bet lots of people missed on this one was to check those two solutions. So k could be 2 or it could be minus 12. Those would both be solutions to that quadratic, but we now need to check that it's actually a solution to the problem that we've been given. Okay, so if we then, sorry, I'm just going to shut something down here that's a bit of a distraction. One moment. Okay. So if k equals 2, we're going to test out what that means. So if k was to be equal to 2, we would then have uv from up at the... Oh, now everything's paused. Okay, there we go. Let me see if I can fit that all on. Okay, so uv from this point just here, if we sub in what k is, that would be 24 minus 4 plus 10 times 2 is 20 times I, because k was 2. So that equals 20 plus 20i. Okay, so that's a reasonable solution to what we've got up here. That would work. We would have 20 on the x-axis and up by 20 on the I direction. So k equals 2 is fine. Now, if k is equal to 12, UV would be 24 minus 144 plus 120 Ki. So that would be, oh, I've done it again, not with the K, just 120 I. Oh, one moment, I've put K equals 12. We want to try K equals minus 12. So we've got 24 minus K squared, which is 144. And then 10 times negative 12 will be minus 120 I. Again, all I'm doing is substituting K equals 12 into that one for UV. So now 24 minus 144, that is negative 120. And we have minus 120 I. Now that one is going to be down in our negative quadrant down here. And, oh, wait, not that one. It'll be this one just here. It'll be across by minus 120 and down by minus 120. So that doesn't give us a solution that matches the situation that we've got, because we wouldn't get an argument of pi by 4. We'd actually get an argument of negative 3 pi by 4 if it was to go over that side. So therefore we discard this one. So this is not a solution. So therefore K is equal to 2 is our final and only possible value for K. Let's just pop that all onto one page. Okay, let's take a look. I did just drop the mark scheme off to one side so we can check that. You would have got an achieved for getting as far as expanding the UV. 2 correct solutions for K would get you a merit, and then all the way through for an excellence. So that means that this line here is achieved, this line here is merit, and your final answer is for the excellence. Okay, no questions coming through on the chat, so I will carry on and we will take a look at differentiation. Okay, we have a closed cylindrical tank. So let's just sketch out what we've got here. Some sort of cylinder where the surface area is equal to 20. And we want to maximize, what are we doing here? We're maximizing the volume. Okay. Let's pop on some stuff that helps us work that out. So we need a radius and we need a height. Okay, next stage. I'm going to take that surface area and work out what that would be algebraically. So we've got a circle on the top and we've got a circle on the bottom. So we would have pi r squared would make one of those circles, and then it's times by 2 to make the lid and to make the bottom. And then we need to add on the curved surface, like the outside of the can. That will be the circumference of the circle multiplied by the height. So that'll be 2 pi r for the circumference and times by h the height. And we're told that that equals 120. Now for volume, what we want to do is find a rate for the volume and then find the derivative of it, set it equal to 0, and then we'd be able to find a maximum, a stationary point. So what we're looking for is to be able to find dV according to something else, and we could go with the R or the H really, but I would find the R easier to do here. Because it would take less pieces to unravel it, because it's within the squared thing already, so you don't really want to be doing square roots and whatnot. Okay, so to be able to do dV by dr and then set it equal to 0, we need something that links the volume and the radius together. Now what we have already is this bit just here, but the problem with this, we can't do an awful lot with that. It gives us the surface area. We want the volume. So volume would be equal to the area of the circle and then multiply it through by the height. So the area of the circle is pi r squared, and we want to times it by the height. Now we can't go straight into differentiating v as it is because we have two different variables. We've got the r and the h. We need to express one in terms of the other so that we've then just got an expression that only has one variable in it. So for that, we're going to use this one here. So I'm going to write h in terms of r. Okay, let's start by moving as much away from h as we can so that we can get 120 minus 2 pi r squared. So then h is 120 minus 2 pi r squared all over 2 pi r. So then if we simplify that one, we end up with, what have we got? Oh, I've just spotted a mistake. I wrote down 120 just there when it should have been a volume of 20. My apologies. So we've got 20 minus 2 pi r squared and 2 pi r. Okay, next, let's try simplify that. So if we divide everything through by 2, we'll have 10 minus pi r squared all over pi r. And if we have the intention of doing some differentiation, we probably want those in two separate terms. So 10 over pi r minus pi r squared over pi r. Well, the pi's will cancel, the r's will simplify, and we're just left with a minus r. Okay, back to our v. And by that I mean our v, not RV. Okay, so let's go to the v, and now we can replace h with its equivalent in r. So that's pi r squared, and we're going to times it by h. 10 over pi r minus r. Okay, so now we have, if we multiply out that first term, the pi's will cancel. One of the r squareds will cancel with one of the r's at the bottom, so we end up with 10r. And then minus pi r cubed. Okay, now finally we're in a point where we can actually differentiate v with respect to r. So dv by dr, well, 10r will differentiate to r, and pi is just a number, remember, so we bring the 3 down and reduce the r power by 1. Now this will give us a maximum when that is equal to 0. So from here, we then have 3 pi r squared is equal to 10. So r squared is equal to 10 over 3 pi, and r is equal to plus or minus the square root of 10 over 3 pi. But to have a minus number doesn't make sense in this context because we're talking about a measurement of the radius. So we don't actually need the plus or minus. It will just be the positive square root of that. And I can't show you the calculator, but that comes to 1.03. And we'll just check the measurements. We're in meters. So we have 1.03 meters. Okay, how are we doing out there? Everybody following along? Any questions as I go, or stages that you want explained a bit more? I'll give you a chance just to type something in the chat in case you want to. And meanwhile, I'll look at where the marks went for that. So we didn't have a particular point that got you an achieved here, but we do have a merit if we give an equation for the volume in terms of one variable. So that was doing this part just here. That's where the merit is turning the volume into something in terms of R. You could equally have done it in terms of H as well, and then you would do dV by dH. It would have looked slightly different, but come to a similar situation, but then at the end you would have had to turn the H, or use the H to figure out the matching radius at that point. So I've stuck with R throughout. Okay, so we have integration left. Now this one is actually very tricky. I'll just sort of forewarn you with this one. It's not that the math so much is tricky, it's keeping track of what is a constant and what is a variable throughout all of this. So on this situation, we've got a particular equation that's given to us where we've got an integral of this thing that represents the energy required to pump the water out of the tank. Now, it's kind of irrelevant what it means. We just need to work with it and these shapes that we have. There's lots of things to do with cones and cylinders when it comes to calculating maximums and what have you. Like you just saw with the differentiation one, it came up on that paper too. So with this one, some things to keep track of is that K is a constant, so it's just a number. H is the height of the water. Now that does vary, so that goes up and down, so that is a variable, and that's a small h. Now the capital H over here that we see and that's inside of here is the maximum, where the height starts at. So that one is a fixed number. That's a constant. We don't know what it is and we're not going to work out what it is, but just remember in your head that that's not a variable. The little h is a variable. Now, a small r is the radius of the water surface at that point in time. So in your cylinder, that doesn't change. As the height goes down, your radius will stay the same across it. But on the cone, it does. So as the height goes down on the cone, then your radius gets smaller and smaller and smaller. So we will need to consider that when we get to that point. And A is something that varies with the h, because the little h changes, the little height changes. It will, as it drops down on the cone, it will change the area that circle is on the surface of the water. On the cylinder, it doesn't change. So there's more that stays the same on the cylinder. So we're going to start with working out the cylinder, because that's a bit of an easier one. So let me just shrink this down and give me a bit more room. So let's start with, in fact, let's see if I can just shove that out of the way. Okay, so the E equation for the cylinder. Right, let's use that integral that we've got just there. So we're using between 0 and h, which is just the number of how high we've gone. So it is a number, it's a constant, we just don't know what it is. And we're going to put in the details that we can for this equation that's given in the question. Okay, so the first line down, we're going to go 0 to h. K is a constant, so we're not changing that. H minus the height, we leave that in terms of h. We're trying to turn everything into something in terms of h now. Now the area of the circle, this bit here, so on a cylinder, that area is going to stay constant as well. So we can turn that one into a constant too. So that will just be pi times the radius squared, because we've been given capital R as the radius of that one, and that's a fixed number. Now we're going to differentiate that with respect to h. Now the only thing in that expression that is a variable is the little h. So we can now do everything with respect to h. Everything else is a constant number. Okay, so let's put that into something that we can differentiate. So multiplying out our terms, we will have k, capital H, pi, r squared, minus k, little h, pi, r squared. And just to make it it's exceptionally clear, I'm actually going to put the pi r squared in front of the little h. Now the only variable in that whole mix, oops, hold on, is this small h here. This term here is entirely a constant, we just don't know what it is. Same with the coefficient of that little h. So if we're thinking in terms of integrating, that first term will be the constant times by the variable that we're differentiating by, which is a little h. And on this second term, we take the h variable, we increase its power by 1, we divide by the new power. I'm going to do that between 0 and h. Okay, hopefully you're still with me. This is a very tricky one. So if you need to go back and watch back a little bit, then feel free to go ahead and do that. Okay, so let's pop in our h into the first thing. Now if I put an h, capital H, into here, because that's the limit that I'm putting in, then I'm going to have it times by the other capital H that's there, so it becomes h squared. Next is to put it into this lowercase h there, and we will have k pi r squared h squared over 2. If I substitute in 0 in both of those, I'm going to get 0. Okay, let's just see if I can tidy this up just a little bit. Okay, back to here. Now, take a look at this term that we have. We've got k pi r squared times by h squared. We've got k pi r squared times by h squared, and then over 2. So effectively what we have is a whole term. That first one is a whole term. Take away a half of it. So we will end up with a half of that term. Okay, so that's E for the cylinder. Now we need to do E for the cone. I'll just scroll up and think about what we've got going on with the cone. We have capital H is the full height, capital R is the full radius, but as the water goes down, we get a different value for R. That lowercase r we were told in the question just here is the radius of the water as it's going down, and the height as it's going down will be a little h. Okay, now because those are similar triangles, we can find a link between them and express r in terms of h. So because of proportionality, if we do little r over big R, that will be the same as little r over big H, which means that small r is equal to little r over h times big R, or in other words, r h over h. So now we've expressed r in terms of h. We can substitute it into the formula that we had before. So E for the cone. So our formula from up here, 0 to h, k h minus little h times the area dh. Let's carry on with that one, but doing it for the cone, we have between 0 and h, k capital H minus little h times by the area. The area will be pi times little r squared because it's changing as it goes down, so we need to use that little r dh. Now we can't integrate that yet because we've got mixed in there the little h and the little r, and both of those are variables. So we need to use what we have over here to express that little r in terms of h. So little r squared is the same as if I do capital RH over h all squared. Or in other words, it's r squared, little h squared, capital H squared. Okay, now everything is in terms of h. We can get on with actually using it and then integrate it. Okay, so expanding that, we have k capital H pi r squared little h squared over h squared minus k pi r squared h squared over capital H squared times by the small h that we had over here, just that one there being multiplied through. Just saw the question coming up on the chat. This is along the lines of related rates of change. The related part here is to do with the similar triangles and being able to turn one variable into something in terms of the other one. That's where it comes into here. But actually what makes this an excellence is the amount of constants we have represented here that make it very confusing. You've got to be really careful as you work it through. Okay, now back to this one here. Let's do some simplifying. So we can cancel the h squared there with the capital H in there. And I think that's as much as we can do. Okay, so if we integrate this one, what we've got as the variable is this h squared. So we increase that variable by 1. So it'll become h cubed and divide by the new variable, which will put a 3 on the bottom. So here we go with h cubed over 3, and there's still a capital H underneath. On this side of things, the h squared times by h becomes an h cubed. If I now integrate this, we have k pi r squared. The h increases by a power of 1, so we have h to the 4. Divide it by the new power, and we've got 4h squared. Okay, now substituting that in. Oh, I forgot to close off the bracket. Here we go. Capital H and a 0. Okay, if we put the capital H in, we will get k pi r squared. Now, the h is going in for the little h. Stay with me, there's lots of h's flying around. So we have capital H cubed all over 3h minus k pi r squared capital H to the 4. Let me just rewrite that. All over 4h squared. And when we put a 0 in, it'll just be a 0. So that's an easy bit. Let's think about what that's telling us now. So that h will cancel with one of those, and so we end up with this being h squared over 3. H squared will cancel with 2 of the h's on the top, so we end up with an h squared here. Now you can spot that the top here, actually let's use a different colour, this top is the same as that top, so effectively what we have is a third minus a quarter of that thing that I've highlighted in yellow. So a third minus a quarter, and you can pop that into your calculator if you're not confident with fractions. A third minus a quarter is just a 12th. So this will be 1/12 of the thing that's in yellow. Remembering again that that thing in yellow is actually just a number. They just haven't told us what those numbers are. All right, we're nearly there. So go back to what we had up here. So this one here, that was for the cylinder. And this one here for the cone. And we have the almost exact same thing. The tops are the same, but the bottom we have a half on the cylinder one and we have a 12th on the cone one. So the cone one is 6 times smaller than the cylinder, which was what was in the question. So therefore, E for the cone is equal to 1/6 of E for the cylinder. Okay, so let's just go back to the question and just show you that's what we were aiming for, was to show that the energy required to empty the conical tank is 1/6 required for the cylindrical one. And that's where we've gone to with that. Now let's take a look at the marking schedule, and I'll show you where each of the points came in for achieved and merit. Okay, so one of those correct integrations done. So that's this point here. There was an achieved just there. The correct energy calculation for the cone here is a merit. Doing both of them correct and making that comparison is where the excellence was. And goodness me, that was a hard one. So if you managed to follow along, well done. That was a particularly tricky one. Not so much because the maths in it is hard or the integration was exceptionally difficult. It's because there was so much notation in there that could very easily be confused as things that you should integrate, but they weren't. They were just constants. Okay, well done. Thank you for everybody that hung in there whilst we went through that harder one. I'll do another one of these excellence ones again tomorrow. I'll post the questions up onto Instagram so you can have a go at them beforehand. And I strongly recommend that you do try them out before I come back and go through them. And yeah, that's us done. Unless you have any burning questions, I'll leave it open just for a second or two to allow for the delay. And I can go through anything that you need of any of the 3 questions that we've just completed. Otherwise, I will see you tomorrow.